Hello everybody, welcome to Type-C Showcase. So this is the first video. I think this will turn into a series where I'll be talking about Type-C programming language, the feature that the language has, and yeah, I think all around Type-C ecosystem. There is a lot more to come in the Type-C language. So yeah, today we're starting with the language showcase. Since it's the first video, it's not going to be a tutorial for new programmers. Obviously, if you're a new programmer, I don't think Type-C is the right language to start with right now because the language is still getting shaped, and yeah, I can't guarantee a good start in programming career with Type-C. So yeah, if you're an experienced programmer or you do know how to program in general, like I think it's a good idea to start with this video because I'm going to go through the syntax, the features, data types, etc. And yeah, hopefully also get some feedback. Type-C is a bit opinionated, and yeah, let's get started. So what you're seeing right now is my own editor that I wrote using Electron and Monaco, same editor as VS Code. Essentially, I am creating a new project here. Let's call it demo 2. Open. There we go. So now we have a project, but we cannot run it just yet because I have to create the editor configuration files. Hit save. It created the output folder. Now we can compile and run, and there is our hello world. So this is what Type-C looks like. This editor has auto-completion support, but it's a bit sluggish, a bit slow, but it has the best support so far. There is a VS Code extension that only supports syntax highlighting, so that's still in the works. For now, I think I'm just going to be using this. Now, syntax Type-C, first and foremost, is that you must have a main function. And this main function, it's similar to C and C++. And this main function, or the file that contains the main, is your entry. So it should be kind of your entry file in the module.json. This is equivalent to package.json if you're a JavaScript programmer. So kind of the same logic here. We can go ahead and get started with, we can start with arguments. So we can have command line arguments, which are going to be an array of strings. And in order to feed arguments, because we are not running the language from CLI, just gonna adjust the layout a bit. There we go. We're not using the CLI command line interface. We're using the editor. So we have to edit config and add some arguments in here. There we go. And let's start by printing these arguments. So what we're going to do is we can start with the for each string in args and println str, compile and run. There we go. So for each, actually, under the hood generates a for loop, not in the bytecode, but actually in the AST, it gets compiled into a for loop AST, and this is the only case where you actually don't need to add a let declaration, because the for loop will automatically define the string for you. It's essentially a macro for a let. I mean, under the hood, you cannot think of it as a macro because it's not, but that's the closest thing. So if you define here another variable str, you will get a warning that, hey, this str shadows an existing symbol. So if we were to do this in a for loop, we would have to use for and then declare a variable I. I'm not going to add the data type actually, and as long as I is less than args.length plus equal 1, the plus plus operator is not yet implemented. So println args of I, then run. Well, we're gonna get the same output, so just gonna add the end in here. There we go. Few important things is that args is an array. It's a basic array because you also have a more dynamic array for the standard library. It's similar to Java arrays. So let's talk about arrays a bit. We can have, for example, vector as a U32 array, and we can add some values. 3. And what can we do with this array? So if we want to add an element, actually let's add for each down here, for each ei in a vector. We're gonna println v of I is gonna be equal to e. I'm gonna remove the end on this. There we go. So if I want to add an element here, actually I think I'm just gonna turn this into a function. So print back. Then there we go. Oh, that's right. What is v? Well, it's a U32 array. Let's remove args here because it will be marked as unused the whole time. So print back vector. And if we want to add new element, well, let's look at the methods we have. We have slice, length, and extend. That's all what the basic array have. And essentially all of these fields will turn into bytecode instructions, specific bytecode instructions for array access. So in order to extend, we have to use extend actually with the new size, which is the new number of elements, not the size t as in C. So 4 elements, and then vector of minus, no, I'll get back to minus in a moment, of 3 equals 4. And then print back vector. There we go. That didn't work. 0, 1, 2, 0, 1, 2, 3. No, it did work. But I set it to 4, didn't I? Oh, I swapped the... Why did I swap the index and the value? So this is actually index and this is the value, so let's call it value here. Oh boy. So it has been like that since the beginning and I just noticed it. All right, 1, 2, 3, 4. That works. I thought it failed for a moment. I was like, what? All my unit tests. Also, we can actually use the negative minus, and here -1. Run, and it works. So this is quite the thing to explain. So actually, when you use a negative index, so I'm just gonna add a comment right here. So when you use, for example, v of I, it will translate into like get, like v index equal I, right? It will get array equal v index equal I. But if you do v of minus I, this will get to this will transform into a reverse get array equal v index equal I. So it's not a negative index per se. It's the whole operation is a reverse index. And that's important because if you use, for example, here, let I equals 1, and then you use minus I, it's not going to be the index of the negative of I. It's going to be the reverse index of I. So I is still going to be a positive number in here. This index is always going to be positive. So it's kind of a new instruction, so to speak, where you have, when you index with a v of negative something, it will result into reverse get of that index equal x. So that's kind of the catch here. Trying to get a Python-like syntax while still maintaining consistency of data types. That's kind of what I've tried to achieve in type C here for arrays. But yeah, that's one cool thing you can do with arrays. But yeah, you can just extend them, slice them, and that's all, essentially. We do have a string class that actually uses an array of bytes. This is the buffer. Kind of everything is stored in here. It's UTF-8. And yeah, essentially, it just when you concatenate a string, it increases the size, adds on top. We also have this array class. Let me see if I can find it. So from std.concatenate containers.array import array. Now did I get that right? If I compile, it should be here. I think it's collections actually. Yep, it is. There we go. So here, this is an array with a fixed size elements, and when you push it, it has like a length and the capacity. It always doubles the capacity, which is kind of like the standard practice. So you don't have to deal with static arrays always, mainly only in the main, because main will always get a static array. All right. So that's about arrays, and we can talk about data types. So let's talk about objects or structs. They are structs. So we can define a point equal struct, and point has like x f32 and y f32, and you can have it t1 is a point, and when you have the type annotation, you can skip enumerating the field and you can just add them in the right order. 1.0f, 2.0f. Then the p2, we're not going to add the type annotation, and in this case we have to explicitly enumerate the field. So x is equal to 1.0, let's make it 10, and 20.0 f. Now this is why. One more thing, if we have z f32 equals 1.0, this is not going to work because 1.0 is a double. You have to add an f for it to be an f32. If you define f64, which is a double, then you can actually add or remove the thing. The f, it doesn't matter because it will be upcasted. So that's kind of the when you have like constants, that's something to keep in mind. And then we're going to have p3, and it's going to be equal to y. It's going to be 200.0f. X is going to be 100.0f, and we can have a c, which is 300.0f. And now we're going to add a function that prints the point. So print point. P, our argument is a point, and it will essentially print ln plus p dot x plus comma plus p dot y. And we're just going to call it for all of these arguments. Print point p1, p2, p3, compile, run. Aha, we have an error. So usually when it says no main function found, it means there is an error somewhere that we are not getting. I'm just going to compile unexpected token, line 9. So I'm just looking at the console output of my editor. What is it? Oh, what is this? That's the culprit. And there we have our points. So it worked, which means, or which showcases that data types, or structs at least in type C, they're matched based on their structure, not necessarily the name. And even if the fields are swapped, as long as their data types match, they will be all good. So the design of structs is something between C and JavaScript. In JavaScript, you have obviously objects, and they're kind of indexed, right? They kind of turn into a hash map in the VM, and yeah, the order doesn't matter because it's a hash map, right? While in C, the order actually matter, and the type must match. So type C is kind of in between, but you can't add dynamically add fields because everything needs to be resolved at compile time actually. And they don't support reflection, or they're not prototype driven, so they're just structs. One more thing, in definition, when you define a struct, actually this is optional. You can completely remove this keyword and it will be, it will recognize that this is still a struct definition. Now, if we were to define a struct as f64, some things here will work, some things won't. P2 will not work. However, I don't know why P3 works. I know why P2 won't work, but out of curiosity, I want to Oh yeah, it still doesn't work. Okay, it's just because there is an error before that. All right, so the reason why P1 works is because it has a type hint, which is point, and then to essentially compare the two types. And so, okay, this is a point, and I expect a point, and I have x f32, so I can upcast it. Y32, so I can upcast it. And since these are like the right-hand side is essentially like a field of constants, they will be upcasted. And P2 doesn't have a type hint. It doesn't have anything to compare to. So then when you're trying to print a point and you have fields that are incompatible, it's not going to work. Another example that will not work is if we have, let's say this is Pn equals, I can actually reuse P2. I can define P4 point equals P2, and this is not going to work as well. Even though I do have the type hint, and I do have a point that contains F32 fields, it's not going to work because these fields are part of an entity already. They're not enumerated. So the compiler will not generate code to upcast all its subfields. Because these fields, they're kind of upcasted at compile time, generate the code to correctly convert 1.0f to 1.0 as in F64. And that's why they're incompatible in this case. So I'm just gonna reverse this. And that's kind of a bit of an review on type checking and compatibility. And it's nested, right? Because it compares the left-hand side with the right-hand side. And then like, okay, so we have a field on the left-hand side, it's F64. On the right-hand side of it's F32. So can we upcast it? If it's a terminal, yes, we can, like here. It's literally a value that, the compiler can change it, like just remove the F, right? But in the other case where you have P4 point equals P2, well, you don't have a terminal anymore, right? Because it's a field within another object. And that's kind of the idea. So yeah, structs, the order doesn't matter. You can have extra fields and still match. It's resolved at runtime, but it uses kind of offset indexing rather than hash map. At least that's how it's implemented currently. It could turn into a hash map later. Just kind of messing around and testing things. Then we can talk about, I think we can end this video with talking about variants, and we can review more types in the next video. We can't review variants without reviewing enums. They're kind of really close, and we will review both of them in a single example. And this example is going to be a tree. So variants, they are algebraic types. So we can create type tree variant, and then our tree could be a leaf node with n value being 32, or it could be a binary with left-hand side that is a tree, right-hand side that is a tree, and an operand that is, we're gonna have to enumerate it. Exactly. It could be a string, but I don't want to do string in comparison. I think we'll review strings in another video. So op type, define enum here. Then we can have add sub formal. Just for simplicity, we're gonna have these three, and op could be op type. All right, and now I want to create a tree. Let's add the type in that it's tree equals, and it's going to be a tree dot binary. The first argument is going to be tree dot binary as well, and the last one is going to be tree dot leaf, and then you can have like 10.0f, and in our binary we're going to have two leaves. We can have, for example, 5 and 1, and we can do an addition, for example. So this is going to be op type.add, and here we can do a mult. So op type.multiplication. That's our tree. So how do we evaluate this? In type C, almost everything can be an expression. I think for loops are the obvious thing that comes to mind that cannot be an expression. So we can have a function eval that requires a tree of type tree, and we can have an equal here. So it's a direct, so this result of this function will be equal to whatever expression we have, and this expression is going to be a match expression. So what exactly are we matching? Tree against a data type. So if it's a tree.leaf with some value v, then it's going to just directly return v. If it's a tree.binary, then we're returning another match here. And exactly what are we matching? So first we need the left-hand side, right-hand side, and the op. So we're actually going to match against the operation that we have. And now we're suddenly matching against the enumeration type. So if it is an op type.add, then we will return eval left-hand side plus eval right-hand side. If it's a subtraction, then it's going to be minus. If it's multiplication, then it's going to be, you guessed it, multiplication. Now, one more thing about pattern matching expressions is that you must always have a wild case in the end. And that's because when the compiler looks at this, when, like, for example, the case of matching against an enum, it cannot really, it's not sophisticated enough to recognize that we have exhausted all of our options. So it doesn't know that. So out of safety, it says, you know, every match case must have a match statement or expression, because pattern matching can also be a statement. So it must always end with an underscore or with a wild case. And in here, we're just going to do unreachable, which will just throw an error at runtime, and it will just say unreachable code reached. Obviously, we can just add a wild case over here because we know if it's a wild case, it's multiplication. But for safety, just going to keep it this way. And we're going to have a wild case here as well. Unreachable. There we go. Now we're going to print eval tree equals plus eval t. So let's do the math. We have 6 multiplied by 10, that's 60. And we have an error. What's in here? Ooh, this is a good one. Yes, so it essentially says cannot use operator plus on left-hand side type unset. And that's because eval is recursive. And again, the compiler isn't sophisticated enough to infer the type of recursive functions. So if it's calling another function, that's fine, as long as the other function is not calling it back, right? But yeah, while it looks at all of the return statements, it cannot really guess. If the function is calling itself, it cannot really guess the type for that. So we have to add a return type. So we added the return type, we run, and we get 60, and that works. So this is all for this video. In the next one, we'll review more data types. Bye.